Hey, welcome back, class. So we're going to start section 9.4. Now we're going to talk about that second type of new function that we haven't seen yet. And you may recall me saying that it is the inverse function of an exponential function, okay? And we actually have a name for it. These functions that we're going to study today are called logarithmic functions. You'll also hear them called logarithms. Okay, so you may have heard that before. So let's just review for a second. So in 9.3 we were discussing exponential functions. Okay, so some function, this f of x is equal to a to the power of x. Okay, and we saw that any sort of exponential function is just some transformation of this basic form, where a is just your base, and a can either be a fraction or it can be a number bigger than 1, okay? But it has to be a positive number. Okay, or we can even express this as y equals a to the x. Okay, I'm going to do it like this because now we've talked about inverse functions. We know, if you remember that four-step process of obtaining the inverse, the first step was to replace f of x with y, and then the second step, and what really created the inverse relationship between x and y, was swapping the x's and y's. Okay, and so if you did that, you'd have x is equal to y to the, x is equal to a to the power of y. Okay, so the x and y trade roles or trade positions, and so now y is an exponent. Okay, whereas previously x was the exponent. Now in doing this, we end up having a function of y, or in other words, x is defined by y. Okay, but as always, we want our functions to be functions of x. And so how do we do this? Well, we solve this guy for y, essentially. Or in other words, we create this function. We say that y is equal to log, or the logarithm, with a base of a of x. Okay. We'll talk later. You'll see later in a later section. If you were to solve this for y, you have to take the logarithm of both sides. Okay, that logarithmic operator will allow you to isolate for y, and so you end up with log base a of x, and that's how you read that. And so this is our new function. This is the inverse of this function up here, okay, or this one right here. So instead of y equals a to the x, we have y is equal to log base a of x. Now I want to point out that whatever the base of that corresponding exponential function was, that will be the base of your logarithm right here. Okay, and when the input for this logarithmic function will essentially have been the output of your exponential function. And then the output of this logarithmic function will be an exponent, just like the input of your exponential function was an exponent. Okay, so we define this new function. We say y is equal to log base a of x, where, and then we use this relation, this inverse relation right here, because this is how we this is the relation that we use to actually evaluate some of these logarithmic functions, at least by hand anyway, where x is equal to a to the power of y. Okay, so you can see here, when you evaluate a logarithmic function, you'll be given this value here. That'll be plugged into the function, and then the function will give you y. Well, y is the exponent. So in other words, you're asking yourself, a to what power is equal to x? Okay, and that's how we're going to go about evaluating these. We're going to do some by hand. I'll show you how you can use the calculator as well. But real quickly, well actually, I'll give you an example here real quick. Think about 2 to the, I don't know, 4th power, okay? 2 to the 4th power is 16. So with an exponential function, this would be like our x, and this would be like our y. Well, with a logarithmic function, the base is still going to be 2, but instead of plugging 4 in for x, you'll be plugging 16 in. So you have log base 2 of 16, and that is equal to 4, okay? Or in other words, what you're asking is 2 to what power? Well, that's supposed to be a question mark. Let me put a little box here. 2 to what power is equal to 16, okay? So mentally, you're kind of reversing the operator, right? Instead of trying to figure out what 2 to the 4th power is, you're trying to figure out 2 to what power would have given me 16. So that's the way you can think about these logarithms, okay? All right, now graphically, remember a to the x looks like this when graphed, okay? Well, if it looks like this if if the base is bigger than 1. If you recall, it's an increasing function, okay? So if your base is bigger than 1, so like if it's 2 or 3 or 4 or 5, then this is what your graph of your exponential function looks like. And we talked about how there's a horizontal asymptote right here on the x-axis, and it crosses the y-axis at 1. Well, the inverse function, or the logarithmic function, we see down here, this is what its graph looks like. And remember how inverse functions exhibit symmetry about this line y equals x right here, okay? So instead of crossing the y-axis at 1, the logarithmic function will cross the x-axis at 1. And it will not have a horizontal asymptote, but it will have a vertical asymptote right on top of the y-axis. Okay? We'll look at a graph later on. But for now, let's look at how can we evaluate some of these logarithms. Okay, the logarithmic functions. So we're going to use that inverse relation, the fact that x will be equal to a to the y, okay? Alright, so example 1, it says find the logarithm, or in other words, evaluate this, okay? So what you're trying to do, the base here is 10, okay? That's going to be your a. Your x is the 1,000, and then this is going to equal y, or the value of your function, okay? Because remember, the way we define this logarithmic function, y is equal to log base a of x. So just identify what your a and your x are and plug them into this inverse relation, okay? And then you'll be able to you'll be able to reason and figure out what y needs to be. Okay, well if I do this, if x is 1,000 and I plug it in over here, then I'll have 1,000 is equal to, and the base is 10, so 10 to some power, okay? So I'm trying to figure out what power of 10 will give me 1,000. And again, this just reiterates the fact that a logarithm, or the output of a logarithmic function, is an exponent. Okay, so we're trying to figure out what exponent of 10 will give me 1,000. Well, think about some powers of 10. 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000. So, log base 10 of 1,000 is 3. Okay? Because 10 to the third power is 1,000. Alright, let's look at example 2. Now sometimes you may see logarithms without a base explicitly written, and anytime that occurs, the base is understood to be 10. Okay, so 10 is actually a very common base for a lot of logarithmic functions, and so similar to how the index isn't written for square root, they don't put a 2. You could if you want, but the square root is so common, we just leave it off. Or similar to how, x has an understood coefficient of 1, but we never really write it, so we know it's there. Well, anytime you just see the logarithm of some number, the base is understood to be 10, okay? And so what we're trying to find here is log base 10 of 10. This is called a common logarithm, because that base is so common. I think I misspelled logarithm. It doesn't have a Y. Okay. Alright, so to figure this one out, our x here is 10. So if I use that same inverse relationship again, a is also 10 because it's the base. X is 10, and then we're trying to figure out the value of y, or in other words, the value of this exponent here. So you're going to think to yourself, 10 to what power is equal to 10? Well, 10 to the first. 10 to the first power is equal to 10. Could have actually written that over here. Okay. 10 to the third power is equal to 1,000. Okay, so the value of this logarithm is 1. Or in other words, the common log of 10 is equal to 1. Okay. Now I'll take this opportunity to show you that in your calculator you actually have a common logarithmic function. It's right here. It just says log. And notice the base here is not written because it's a common logarithm. So the common logarithm of 10 is equal to 1. You could have done the other one the same way because it's a common logarithm as well, right? Because its base is 10, so you could say common log of 1,000 is equal to 3 because 10 to the third is 1,000. Alright, now let's look at some more, a little more complex ones. So it says find the logarithm. So here, interestingly, what we have in place of x is this exponential expression, 3 to the fourth, okay? And then the base, in this case, is 3. And so again, if I think about that same relationship, my x is 3 to the fourth equals, my base is 3 to some power, so I'm trying to figure out this power for y. Well, it's really already apparent. The exponent is already given, okay? You can see that to make these two sides equal, y has to have a value of 4. Or in other words, 3 to the fourth can only be equal to 3 to the fourth. So the value of log base 3 of 3 to the fourth is 4. Or in other words, guys, when it's written like this, the exponent is already there. So you know what the power of 3 has to be. It has to be 4. Okay. Another way you can think about this is whenever the logarithm of the base and the logarithm of your exponential expression in here are the same, then it's just going to be that exponent. This is a property that we'll talk about later on. Okay. Alright, well you might ask, well how do I do this one in the calculator if I wanted to? Well, if you come over here to math, and let's see, come over here to number, if I can remember, no I don't think, now go to math, I think you got to scroll down, yeah here it is, where it says log base. This just will allow you to type in your own base. So when I do that, I can type in my base of 3 And then this, by the way, is called the argument of the logarithm, and it's 3 to the 5th power. And then you can check it, and you'll get 4. Okay. All right, what about example 4 here? Log base 7 of 1. Okay. So guys, I'm going to probably eventually kind of quit writing this over and over and over. The base is 7. This is going to be equal to 1, and we're trying to figure out the exponent. In other words, the base here, 7, raised to what power is equal to 1? Okay. Well, we talked about this last class. It has to be 0. That's the only exponent that you can give 7 and have it be equal to 1. 7 to the 0 power is equal to 1. So in other words, log base 7 of 1 is equal to 0. In fact, guys, the log of 1 is always 0, because it doesn't matter what the base is. Any base raised to the 0 power will always be 1. So any logarithm of 1 is always going to be 0. I'll rewrite that 7 real quick. There we go. Alright, so now let's look at some that are a little more challenging. Alright, example 5. So this one, the argument is actually a fraction. So here we're trying to figure out 3 to what power is equal to 1 over 27. Okay, so you have to be a bit innovative to figure some of these out. What you can do though is, if you can figure out a way to express this left-hand side as 3 to some power by manipulating it, then you'll know what that exponent is, and you'll know what the logarithm here is. So the first thing I notice, and this is probably just from being a math teacher for years, is that 27 is actually a power of 3. 27 is the same as 3 to the 3rd power. So I could start by saying, okay, well, I can express this as 1 over 3 to the 3rd, because that's 3 to the 3rd is 27. And then I could go a step further and I could say, well, I could move this 3 to the 3rd up to the numerator simply by changing the sign of the exponent. We talked about this last class. So instead of 1 over 3 to the 3rd, I could just simply write 3 to the negative 3rd. Okay? And so by doing that, I have expressed that left-hand side as a power of 3. And so now I can answer this question because I know what that exponent is. It's negative 3. Okay? So log base 3 of 1/27 is negative 3. And by the way, guys, anytime you're trying to find the logarithm of a fraction, you're always going to get a negative number. Okay? Because you're talking about figuring out this base right here to what power will give me this fraction. Well, this fraction is always going to be less than 1. The only way that can happen is if that exponent is negative. Alright, but you can do this or check in the calculator as well. If I go to math, and scroll down, we've got a base of 3, and then the argument, or our input, our x in this case for this function, is the fraction 1/27, okay? And hit enter, and we get negative 3. Alright, so what about example 6? I think doing these by hand, even though they're easily done using the calculator, doing these by hand is a good educational process, and just, knowing how to manipulate these, a good exercise. Alright, so example 6. So here, interestingly, the argument is actually a radical. Okay, so here we're trying to figure out 4 to what power is equal to the cube root of 4. Okay. So what I'm trying to do is I'm trying to rewrite this left-hand side as 4 to some power. Once I figure out that power, then I know the value of this logarithm. And another thing I notice is that there's already a 4 over here. However, it doesn't have a power. It's a cube root. It's the cube root of 4. Well, there's a property that relates exponents to radicals. And it's this property right here. If you have the, let's say you have some root of x to the power of b, okay, or sometimes it's better written. Let me rewrite it. Well, yeah, no, that'll be okay. Okay, the 8th root of x to the power of b. Well, you can convert this into an exponential expression. It goes like this. Actually, I want to swap these two. I want to make this you'll see why here in a minute. I want to make the index b, and I want to make the exponent of a, or excuse me, the exponent of x a. Okay. And so anyway, the corresponding exponential relation is x to the power of a over b. So this is the property that you have to use. This property relates radicals to exponential expressions, or vice versa. Okay. In other words, it allows us to rewrite a radical using an exponent. And so that's what we can do over here. Okay, you just need to figure out what your a and your b are. B is always going to be the index, and a is just the power of your radicand. Well, the power here is an understood 1. So once I know that, I can re-express this as 4 to the 1/3 power. Okay, and by doing so, I've figured out what that exponent is. It's 1/3. So I can then restate that log base 4 of the cube root of 4 is equal to 1/3. Okay. My computer froze. Okay, all right, we're back. Okay. All right, well, let's look at example 7. I'm going to go a little bit longer, I think, in this video. Yeah, I think I'm going to get down here to this change of base. That's where I'll stop. So let's look at example 7. Log base 81 of 3. This one I think is probably the most challenging one if you're doing it by hand, because you're trying to figure out 81 to what power is equal to 3. And this is kind of tough, okay, because only really by having a fair amount of familiarity, or having worked with numbers a lot, I know that sorry about that. I know that 3 is actually the 4th root of 81. Or in other words, because what I'm trying to do here is I'm trying to re-express the left-hand side, or 3 in other words, as 81 to some power. That's what I'm trying to find, the power of 81 that's equal to 3. Well, I know that the 4th root of 81 is 3. And so, like I said, this just comes from having had a lot of familiarity over the years. Okay. The 4th root of 81 is the same as 3. Or in other words, 3 to the 4th power is 81. Okay. And so once I can get there, then I can rewrite this as 81 to some power using this property up here that we talked about. Okay, a little understood exponent is 1, so I can rewrite that as 81 to the 1/4 power. Okay, and by doing that, I now see that that exponent has to be a fourth. Okay, so this is equal to 1/4. This one's a little more challenging. Okay, you can do it in your calculator as well. I want to show you something though. So if I do it in the calculator, because the answer is actually a fraction, it may give me a decimal. Okay, so log base 81 of 3, when I hit enter, I get a decimal. So you're going to have to know that 0.25 is the same as a fourth. But remember, you can convert these decimals to fractions, okay, if they're rational numbers, of course. So anyway, all right. Well, now let's talk about another. We talked about this common logarithm at the beginning, and how anytime you saw this log without a base written, it was understood to be 10. Well, there's another logarithm if they leave the base is typically not written. And it's this one here, log base e. So we've talked about that special irrational number e. It turns out, guys, that number occurs a lot in math. And so when we have a logarithm with that base, we tend not to write it. Some books you'll see it written, but usually you just see it expressed this way. Instead of writing log base e of x, it's expressed the natural log of x. Now you may think the acronym here is backwards, but it's not, because it's actually French. Okay, but just think the natural log. Okay, natural log because e is a number that we find in the natural world. Okay, so that anytime you see the natural log of x, understand that that just means log base e of x. And so when we want to evaluate some of these logarithms, some of these natural logarithms, we just need to remember that there's a little understood base of e. Okay, so like this one, for example. There's a little understood base of e down there, then I'm asking myself, e to what power is equal to this argument, e to the third? Well, the power's given to me again. Like a previous example that we saw, that power has to be 3. E to the third can only be equal to e to the third. Okay? So in other words, the natural log of e to the third is 3. And you do have this operator, or this function in your calculator. It's right here, this natural log. So the natural log of, you put in there e to the third power, and it's 3. The reason these two keys are in here is because they're in a sense, they're the most common or most frequently occurring logarithms. Log base 10, or the common logarithm, and then the natural logarithm. Okay, so it's kind of like we have shortcut keys for those two. Alright, well, let's do a couple more here. Example 9. Now sometimes you may not be able to evaluate these by hand. So this is the natural log of 20. So we know the base is e, so we're trying to figure out e to what power is 20. Okay. Well, because e is an irrational number, guys, the value of this exponent is also going to be irrational. And so the only way we can really evaluate this one or get an approximation is by using the calculator. We're going to get a decimal. So this one you have to use the calculator for. The natural log of 20, you hit enter, it's approximately equal to, Okay, so I use the wavy equal sign to show that we're talking about an approximation. Approximately equal to, notice this decimal. There's no pattern here, right? And the digits will go on forever. So that means our answer is an irrational number. Well, I'm going to round it to maybe 4 decimal places. So 2.9957. 2.9957. This just means that if I raise e to this power right here, I'll get something real close to 20. Let's actually check this. If I take e and I raise it to this power, I can actually input this previous output from the calculator in here by saying second and then hitting the answer key. We'll take this answer and plug it in for the exponent. So when I do that, hit enter. Well, my computer froze again. I hit enter, I actually get 20. It froze yet again. Alright, there we go. Okay, but it looks like I'm frozen. That's okay, because we're about to quit the part 1 video. Okay. Now, if I had just used e to the 2.9957, that would have given me something real close to 20, but it wouldn't have been exactly 20. Alright, and then the last thing, look at this one, the natural log of negative 94. Well, if you come back up here and look at the graph of a basic logarithmic function, if you remember, I said there's a vertical asymptote right here. And so what that means is that this logarithmic function can't cross that, can't cross the y-axis. In fact, its domain is only positive numbers. And that corresponds with the fact that the range for your basic exponential function was only positive numbers, because your exponential function sits completely above the x-axis. So your logarithmic function will sit completely to the right of the y-axis, meaning the range, or excuse me, the domain of a logarithmic function, unless it's been transformed or something, is only positive numbers. Okay, we can even put this in here. The domain, we'll talk about this again, for a logarithmic function goes from 0 to infinity, but it doesn't include 0. Okay, so when you have something like this last example, the natural log of a negative number, then you just say that this does not exist. Or, well, I guess in a sense, it's not real. Okay, it's not a real number, and your calculator will actually tell you that. It'll say like domain error or non-real answer. Okay. In short, just remember you can't take the logarithm of a negative number. Okay. And again, as this last sentence said, the logarithm of a negative number doesn't exist because negative numbers are not in the domains of logarithmic functions, or at least a basic logarithmic function anyway. Okay. Alright, so I think I'm going to stop there for the part 1 video.